Introduction. The dinner is quite delicious and I'm enjoying it very well.
Yes, Dad. I agree with you. I'm also enjoying the dinner.
Son, please pass me the salt.
Sure, Dad.
Son, will you answer my one question?
Yes, Dad. I will try to.
Okay, so tell me, why the sugar and salt particles have different structures?
Maybe due to different constituent particles?
Son, your answer is right, but not appropriate. I will tell you. Every structure depends upon the nature of chemical bonding between them. In sugar, there is covalent bonding in the molecules, whereas in salt, there is ionic bonding in the molecules.
Okay, Father. I got the reason and I want to know some more about that.
Students, today we will study more about the chemical bonding and molecular structure. Objectives. At the end of this lesson, you will be able to define chemical bonding, understand octet rule and Lewis symbols, define ionic bond, know about the factors affecting the ionic bond, explain properties of ionic compounds, define bond parameters, describe resonance structure, know about polarity of bonds. Definition. Most of the substances in nature exist in the form of molecules, which are the cluster of atoms of same or different kinds. The attractive force which holds various constituents together in different chemical species is called chemical bond. The chemical bonds can be classified into various types like ionic bond, covalent bond, coordinate bond, metallic bond, hydrogen bond, and van der Waals forces. Coastal-Lewis approach to chemical bonding. The developments in the field of atomic structure provided foundations for various theories of valency. The initial contributions in this field came from W. Coastal and G. N. Lewis in 1916. They were the first to provide some logical explanation of valency, which was based on the inertness of noble gases. Octet rule. The rule states that atoms of various elements enter into chemical combination so as to attain the configuration of 8 electrons in their outermost shell. They do so either by transference of electrons or by mutual sharing of electrons. Lewis symbols. According to these notations, the symbol of the element represents the nucleus as well as the electrons in the inner shells. The electrons in the outer shell are represented by dots surrounding the symbol. The number of dots represent the number of valence electrons. The common valencies of the element can be calculated from the valence electrons. The common valency of the element is either equal to the number of dots or 8 minus the number of dots. For example, the common valencies of lithium, beryllium, boron and carbon are 1, 2, 3 and 4 respectively, while those of nitrogen, oxygen, fluorine and neon are 8 minus number of dots, that is 3, 2, 1 and 0 respectively. Example on Lewis symbols. Let's take an example on Lewis symbols. Use Lewis electron dot symbols to represent the transfer of electrons from magnesium to fluorine atoms to form ions with noble gas configuration. Let's see the solution. The Lewis symbols for the atoms are: the Mg atom loses 2 electrons to attain a noble gas configuration, but F atom can accept only 1 electron to fill its valency shell, so 2 F atoms must take part in electron transfer. We can represent this electron transfer as ionic bond. Ionic bond is formed by the transference of 1 or more electrons from one atom to the other. Generally, this type of bond comes into existence between a metal and a non-metal atom. The metallic atom loses its valency electrons and changes into a positive ion called cation, while a non-metallic atom gains electrons and gets converted into negative ion called anion. The oppositely charged ions are held together by electrostatic force of attraction. Ionic bond may be defined as the electrostatic force of attraction holding the oppositely charged ions. Energy changes during the formation of ionic bond. The formation of ionic bond proceed in following three steps. Step first, formation of gaseous cation. The energy required for this step is called ionization energy. Step second, formation of gaseous anion. The energy released from this step is called electron affinity. Step third, packing of ions of opposite charges to form ionic solid. The energy released in this step is called lattice energy. Now, for stable ionic bonding, the total energy released should be more than the energy required. The conditions for the stable ionic bonding are: ionization energy of cation forming atom should be low. Electron affinity of anion forming atom should be high. Lattice energy should be high. Differences between ionic bond and covalent bond. Ionic bond is formed by transference of electron from one atom to another, whereas covalent bond is formed by mutual sharing of electrons between the atoms. Ionic bond usually exists between metal and non-metal atoms, whereas covalent bond usually exists between non-metal atoms. Ionic bond is non-directional, whereas covalent bond has directional character. Ionic bond is always polar, whereas covalent bond may or may not be polar. Ionic bond holds charged particles of opposite charges, whereas covalent bond holds neutral particles. No multiplicity is observed in ionic bond, whereas covalent bond can be single, double or triple bond. Factors affecting the ionic bond. The factors which favor the formation of ionic bond and also determine its strength are following. Ionization energy. In the formation of ionic bond, a metal atom loses electron to form cation. This process requires energy equal to the ionization energy. Lesser the value of ionization energy, greater is the tendency of atom to form cation. Electron affinity. It is the energy released when gaseous atom accepts electron to form a negative ion. Thus, the value of electron affinity gives the tendency of an atom to form an ion. Greater the value of electron affinity, more is the tendency of an atom to form an ion. Lattice energy. Once the gaseous ions are formed, the ions of opposite charges come close together and pack up three-dimensionally in a definite geometric pattern to form ionic crystal. This process is accompanied with the release of energy referred to as lattice energy. Thus, lattice energy is defined as the amount of energy released when 1 mole of ionic solid is formed by the close packing of gaseous ions. The magnitude of lattice energy depends upon the following factors. Size of the ions. Smaller the size of ions, lesser is the internuclear distance and greater will be the interionic attraction. Hence, larger will be the magnitude of lattice energy. Charge on the ions. Larger the magnitude of charge on the ions, greater will be the attractive force and higher is the value of lattice energy. Properties of ionic compounds. The common properties of ionic compounds are following. They are bad conductors of electricity in solid state, but are good conductors of electricity in molten or dissolved state. The chemical reactions between the ionic compounds involve the combination between the ions furnished in the aqueous solutions. Such reactions are called ionic reactions. Generally, ionic compounds exist in the form of crystalline solids. They have high melting and boiling points. It is due to very strong electrostatic force of attraction between oppositely charged ions. They are soluble in water and other polar solvents which have high dielectric constants. They are insoluble in non-polar solvents. Bond length and bond angle. Bond length. It is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. The covalent radius is measured approximately as the radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. The van der Waals radius represents the overall size of the atom, which includes its valency shell in a non-bonded situation. Bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule ion. Bond angle is expressed in degree. Bond enthalpy and bond order. Bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. Bond order. The bond order is given by the number of bonds between the two atoms in a molecule. With increase in bond order, bond enthalpy increases and bond length decreases. Resonance structure. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structure of the hybrid which describes the molecule accurately. When a molecule can be represented by more than one Lewis formulae, none of which is able to explain all the observed properties of the compound, then the actual structure of the molecule is intermediate of the various Lewis formulae and is called resonance hybrid. Polarity of bonds. In ionic bond, the cation tends to polarize the electron cloud of the anion by pulling electron density towards itself. This causes development of covalent character in ionic bond. Smaller the cation, higher is its polarizing power. Cations with pseudo-noble gas configuration have relatively high polarizing power than those with noble gas configuration. Larger the size of an ion, higher is its polarizability. Difference between metallic bond and covalent bond. The simultaneous force of attraction between the mobile electrons and the positive kernels constitutes a metallic bond, whereas the mutual sharing of electrons between the combining atoms of the same or different elements is called a covalent bond. Metallic bond is a non-directional, whereas covalent bond is directional. Metallic bond is a weak bond because mobile electrons are simultaneously attracted by a large number of kernels, whereas covalent bond is a strong bond because the bonded electron pair is strongly attracted by two nuclei. Did you know? In metallic bonds, huge number of atoms lose their electrons. They are held together in a lattice by the attraction between free electrons and positive nuclei. The difference of energy between the resonance hybrid and the most stable resonating form is called resonance energy. Pure ionic bonding is not known to exist. All ionic compounds have a degree of covalent bonding. Summary. Let us summarize what we have learned. The attractive force which holds various constituents together in different chemical species is called chemical bond. Octet rule states that atoms of various elements enter into chemical combination so as to attain the configuration of 8 electrons in their outermost shell. In Lewis symbol notations, the symbol of the elements represents the nucleus as well as the electrons in the inner shells. The electrons in the outer shell are represented by the dots surrounding the symbol. Ionic bond may be defined as the electrostatic force of attraction holding the oppositely charged ions. Electron affinity is the energy released when gaseous atom accepts electron to form a negative ion. Lattice energy is defined as the amount of energy released when 1 mole of ionic solid is formed by the close packing of gaseous ion. Bond angle is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule ion. Bond angle is expressed in degree. Bond enthalpy is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state.
Introduction. Life depends upon hydrogen bonding. Life is created from water, and water is a liquid due to hydrogen bonding in its molecules. If there is no hydrogen bonding, then water must be a gas just like air. There would be no oceans, no lakes, and no rivers. The fluids in cells of living bodies also exist due to hydrogen bonding. So, all the living systems depend upon hydrogen bonding. Students, you must be curious to know more about this. Today we will study more in our chapter Chemical Bonding and Molecular Structure. Objectives. At the end of this lesson, you will be able to explain VSEPR theory, describe valence bond theory, define hybridization, know about types of hybridization, explain molecular orbital theory, understand electronic configuration and molecular behavior, analyze bonding in some homonuclear diatomic molecules, define hydrogen bonding. Valence shell electron pair repulsion, VSEPR theory. VSEPR theory provides simple explanation for the geometrical shape of different molecules. The central atom of molecules may contain two types of electron pairs. They are bond pair and lone pair. The main points of this theory are: the electron pairs surrounding the central atom repel each other. The geometry and shape of the molecule depend upon the number of electron pairs in the valence shell of the central atom. The repulsive interactions between two lone pairs are different from those between two bond pairs or those between a lone pair and a bond pair. Structure of molecules according to VSEPR theory. Shape of some simple molecules are AB type. This type of molecule is always linear. AB2 type. In this type of molecule, the central atom contains only two bond pair electrons, and these electron pairs will repel each other to attain minimum energy, will remain at 180-degree angle. AB3 type. In planar trigonal structure, the central atom contains only three bond pair electrons, and to minimize the repulsive force, the electron pairs will be arranged at vertices of an equilateral triangle, and the angle is 120 degree. In pyramidal structure, the central atom contains a lone pair and three bond pair electrons due to unequal repulsion. The electron pairs will be arranged at the apexes of a distorted tetrahedron, and the angle is 107 degree. AB4 type. They have regular tetrahedral structure. In this type, the central atom contains four bond pair of electrons, and to minimize repulsive force, the electrons are arranged at the apexes of a regular tetrahedra, and the bond angle is 109.5 degree. AB5 type. In this type, the central atom is surrounded by five bond pair of electrons, and to minimize the repulsive force, the most stable arrangement is trigonal bipyramidal. AB6 type. In this type, the central atom contains six bond pair of electrons, and to minimize the repulsive force, they are arranged at the apexes of a regular octahedron. Valence bond theory. According to this theory, covalent bonds are formed due to mutual overlapping between two atomic orbitals. Greater overlapping ensures the stability of the covalent bond. Extent of overlapping depends upon nature of orbitals and nature of overlapping. Overlapping increases if the orbital remains closer to the nucleus. since except s orbitals, all other orbitals have directional property. In case of two subshells of equivalent energies, the subshell having more directional property shows greater extent of overlapping. S orbitals show only head-on overlapping. P orbitals show both head-on overlapping as well as lateral overlapping. In head-on overlapping, the overlapping region is more than lateral overlapping. Therefore, stronger bond is formed due to head-on overlapping. Types of covalent bond. The covalent bond may be classified into two types depending upon the types of overlapping: sigma bond and pi bond. Sigma bond. Sigma bonds are formed due to head-on overlapping between two half-filled atomic orbitals along the nuclear axis. Sigma bonds are formed due to different types of overlap. SS overlap. Hydrogen molecule is formed due to overlap of s orbitals of two hydrogen atoms. The partially filled s orbital of one H atom overlaps with partially filled s orbital of another H atom. This type of overlapping has no directional character. S-P overlap. Sigma bond may form due to overlap between s orbital of one atom and p orbital of another atom. Such type of overlapping takes place during formation of HF molecule. This type of overlapping has directional character. P-P overlap. During formation of F2 molecule, half-filled p orbital of one fluorine atom overlaps with half-filled p orbital of another fluorine atom. This type of overlapping has also directional characteristics. Pi bond. Pi bonds are formed due to lateral overlapping between two atomic orbitals along the perpendicular direction of the internuclear axis. This type of overlapping takes place only in case of two p orbitals, the overlapping zone being small. Hence, pi bond is a weak bond. Difference between sigma bond and pi bond. Sigma bond is formed by the axial overlap of atomic orbital, whereas pi bond is formed by the sidewise overlap of atomic orbitals. Sigma bond can be formed by overlap of SS, SP or PP orbitals, whereas pi bond involves the overlap of p orbitals only. Sigma bond is stronger because overlapping can take place to a larger extent, whereas pi bond is weaker because the overlapping occurs to a smaller extent. In sigma bond, the molecular orbital is symmetrical about the internuclear axis and consists of single charged cloud, whereas in pi bond, the molecular orbital is discontinuous and consists of two charged clouds above and below the plane of atoms. Sigma bond may be present between two atoms either alone or along with pi bond, whereas pi bond is always present between two atoms along with the sigma bond. The shape of molecule is determined by the sigma framework around the central atom, whereas pi bonds do not contribute to the shape. However, they modify the dimensions of the molecule. Hybridization. It is a process of intermixing of atomic orbitals with small difference in energy and belonging to the same atom at the same time of bonding so as to give another set of orbitals with equivalent shapes and energies. Different types of hybridization depend upon the type of atomic orbitals which are used for intermixing. Orbitals participating in hybridization must have only small difference in their energies. The number of hybrid orbitals is equal to the number of orbitals participating in hybridization. Hybrid orbitals form sigma bonds and are stronger than pure atomic orbitals. Types of hybridization. The various types of hybridization involving s, p and d orbitals. The different types of hybridization are following. sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. sp2 hybridization. In this hybridization, there is involvement of one s and two p orbitals in order to form three equivalent sp2 hybridized orbitals. sp3 hybridization. In this type of hybridization, there is mixing of one s orbital and three p orbitals of the valence shell to form four sp hybrid orbital of equivalent energies and shape. Example. Let's take an example on hybridization. Which hybrid orbitals are used by each carbon atom in the following molecules? Let's see the solution. In this molecule, carbon atoms using sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. Molecular orbital theory. In molecular orbital theory, orbitals are devised for the molecules as a whole. These orbitals consist of nuclei of all the combining atoms lying at a fixed equilibrium distance. Thus, atomic orbitals are monocentric, whereas molecular orbitals are polycentric. Molecular orbitals are formed by combination of atomic orbitals of nearly same energy and proper symmetry. Number of molecular orbitals is equal to the number of combining atomic orbitals. Among the new molecular orbitals formed, half are of lower energy and other half are of higher energy. The molecular orbitals are filled in accordance with the AU-FB-AU principle, obeying the Pauli's exclusion principle and the Hund's rule. Linear combination of atomic orbitals, LCAO. According to Schrödinger's wave equation, an atomic orbital can be represented in terms of its wave function psi, which corresponds to amplitude of the corresponding three-dimensional electron wave. A linear combination of two atomic orbitals can be achieved by addition and subtraction of two atomic orbitals of the individual atoms. If for two atoms A and B, each containing one electron, their wave functions are represented by psi A and psi B respectively. Molecular orbitals of the covalent molecule AB can be represented by psi B is equal to psi A plus lambda psi B.
Psi A
is equal to psi A minus lambda psi B, where psi B is equal to bonding molecular orbital. Psi A is equal to anti-bonding molecular orbital. Lambda represents partial ionic character of AB molecule. Bonding molecular orbit is of lower energy than the atomic orbitals as the electrons feel greater attraction between them. Anti-bonding molecular orbit is of higher energy than the atomic orbitals as the electrons feel less attraction between them. Types of molecular orbitals. Molecular orbitals are designated as sigma, pi, delta instead of s, p, d, etc. in atomic orbitals. Sigma molecular orbitals. Molecular orbitals which are cylindrically symmetric around the bond axis are known as sigma molecular orbitals. Pi molecular orbitals. These orbitals are formed due to lateral overlap between two p orbitals along the perpendicular direction of the bond axis. Electronic configuration and molecular behavior. The distribution of electrons among various molecular orbitals is called the electronic configuration of the molecule. Bond order. Bond order is defined as 1/2 the differences between the number of electrons present in the bonding and the anti-bonding orbitals. A positive value of bond order signifies the stability of a molecule, and a negative or zero bond order indicates that the molecule is unstable or the molecules will not form at all. Higher bond order indicates higher bond dissociation energy and shorter bond length. Bond order indicates the number of covalent bonds in the molecule. Some properties of molecule. Stability of molecule. If Nb is the number of electrons occupying bonding orbitals and Na is the number occupying the anti-bonding orbitals, if Nb is greater than Na, the molecule is stable. But if Nb is less than Na or Nb is equal to Na, the molecule becomes unstable. Nature of bond. Integral bond order values of 1, 2 or 3 correspond to single, double or triple bonds respectively. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Magnetic nature. If the electronic configuration of a molecule contains unpaired electrons, then the molecule will be paramagnetic, and if it contains only paired electrons, then the molecule will be diamagnetic. Bonding in some homonuclear diatomic molecules. Hydrogen molecule H2. The value of bond order is 1. The molecule is stable and diamagnetic. Helium molecule He2. The value of bond order is 0. The molecule is unstable and diamagnetic. Oxygen molecule O2. The value of bond order is 2. The molecule is stable and paramagnetic. Number of covalent bonds is equal to 2. Nitrogen molecule N2. The value of bond order is 3. The molecule is stable and diamagnetic. Number of covalent bonds is equal to 3. Hydrogen bonding. It is electrostatic force of attraction existing between covalently bounded hydrogen atom of one molecule and the electronegative atom of the other molecule. This bond comes into existence when hydrogen atom is directly bonded to high electronegative atom. The bond is represented by dotted line. For more effective hydrogen bonding, the hydrogen atom should be linked to the atom with small size and high electronegativity. Hydrogen bond is weaker than ionic, covalent, dative and metallic bonds, but stronger than van der Waals forces. Types of hydrogen bonds. There are two types of hydrogen bonds as following. Intermolecular hydrogen bond. Hydrogen bonding occurring between molecules of same or different substances is termed as intermolecular hydrogen bonding. It causes association of molecules, increase in melting and boiling points, solubility of molecular substance like alcohol, sugar and honey in water. Intramolecular hydrogen bond. Hydrogen bonding occurring within the same molecule is termed as intramolecular hydrogen bonding. O-nitrophenol, salicylic acid are some examples of intramolecular hydrogen bonding. Did you know? Covalent compounds are usually insoluble or less soluble in water. Energy of the separate helium atoms is smaller than that of the system when they are close to each other. They prefer to stay separate and do not form He2 molecule. A water strider or skater bug uses the surface tension of water made by hydrogen bonds to move around. Summary. Let us summarize what we have learned. The geometry and shape of the molecule depend upon the number of electron pairs in the valence shell of the central atom. The repulsive interactions between two lone pairs are different from those between two bond pairs or those between one lone pair and a bond pair. According to valence bond theory, covalent bonds are formed due to mutual overlapping between two atomic orbitals. Sigma bonds are formed due to head-on overlapping between two half-filled atomic orbitals along the nuclear axis. Pi bonds are formed due to lateral overlapping between two atomic orbitals along the perpendicular direction of the internuclear axis. Hybridization is a process of intermixing of atomic orbitals with small difference in energy and belonging to the same atom at the time of bonding, so as to give another set of orbitals with equivalent shapes and energies. Hydrogen bonding is electrostatic force of attraction existing between covalently bounded H atom of one molecule and the electronegative atom of the other molecule.